Here in section 12.5, we're going to look at the normal curve. And so the normal curve, the normal distribution, is when data is normally distributed. It means it's not skewed left or right, it's not bimodal. It's normally distributed, means it creates a bell-shaped curve. A bell-shaped curve called a normal curve. And so we get our data in what looks like a very bell-shaped curve. And so the bell-shaped curve, the normal distribution, the data is symmetric about a vertical line through the center. So let's assume that I can draw well enough that both sides are identical, that the curve, the data is symmetric about this line down the center. It also turns out that the mean, the median, and the mode are all the same in a normal distribution, and they're all the center of the data. We know they're the center of the data, but they actually fall on this line that the data is symmetric about. So this is going to be your mean, your median, and your mode. We're mostly worried about it being the mean, but it just turns out that it is also the median and the mode of that set of data. And it's very normally distributed. The left side is identical to the right side. You get a majority of your data centered here around X, and then it kind of tails off to the edges. So when our data is normally distributed, when it's bell-shaped, when it's symmetric about the mean, median, and mode down the center, we can use what's known as the empirical rule. Now, the empirical rule is only for normal distributions, but it tells us if we have a normal distribution, then 68% of the data lies within one standard deviation of the mean. So here's the mean. And so within one standard deviation above and below the mean, within one standard deviation on either side. So this is one standard deviation plus 1s, and this is minus 1s from the mean. One standard deviation above, one standard deviation below. That tells us between here and here, we have 68% of our data. Well over half of our data falls within one standard deviation of the mean. And so notice that if from here to here is 68%, and it's symmetric about this line, then that tells us that this half is going to be identical to this half, that this line cuts it in half. So if the whole thing is 68%, that tells me 34% of my data falls here, and 34% of my data falls here. Now, the normal distribution also says that 95% of the data lies within two standard deviations of the mean. That means if I take my mean, I add one standard deviation, I add a second standard deviation. I take my mean, I've subtracted one standard deviation, I subtract a second standard deviation. Then between this value and this value, I have 95% of my data. The vast majority of your data falls within two standard deviations of your mean. And then lastly, 99.7% of the data lies within three standard deviations of the mean. So here's my mean. I added 1, 2, 3 standard deviations. And then again, the mean, I subtracted 1, 2, 3 standard deviations. And so we get almost all of our data. We get 99.7% of our data falls between this value and this value. 3 standard deviations above or below the mean. Now going back and looking and filling in, like we filled in the 34% and the 34% here, we can fill in each of the rest of these as well. Because notice if we have 95% of our data falls between here and here. Well, we've already taken care of 68% in the center. So if we subtract the 95 minus the 68, that leaves a remaining 27% that has to be split between these two. And because it's symmetric, it's going to be split evenly. That means 13.5% here and 13.5% here. And you'll notice that if you add those up, the 13.5, the 34, the 34, and the 13.5, you do get 95% of your data. So 13.5% falls here, 34% here, 34% here, and 13.5% here. We can do the same thing. We know that 99.7% of our data fall between here and here. Well, again, we've already taken care of 95% of it in here. So if we subtract, that leaves us 4.7% that gets split between this piece and this piece. Again, it's going to be split evenly. That puts 2.35% of your data here and 2.35% of your data here. And then remember, with percents, our total is 100. So with 100%, if 99.7 falls within here, and we have to have a total of 100, that leaves us 0.3% out here in these little tails. So again, split evenly because it's symmetric. Half of 0.3 would be 0.15% for each of these tails. And so now if we add all these percentages up, we do get the 100% that we expect. And so we can see where all of our data will fall. All right, some examples of how we use this empirical rule. You work in the summer as the mathematical consultant for a light bulb factory. The boss wants to know what percent of the light bulbs will last between 950 and 1,150 hours. You know that the mean life is 1,050 hours and the standard deviation is 50 hours. Make a sketch of the distribution and make an estimate for your boss. So we know it's normally distributed. And so if we draw the sketch, we know it's going to be a bell-shaped curve. Again, assume I can draw them nice. We know down the center is where our mean goes. We know the mean is 1,050, so that goes in the center. We know that we're going to add 1, 2, and 3 standard deviations above the mean. We know we're going to subtract 1, 2, and 3 standard deviations below the mean. Well, they tell us the standard deviation is 50. So if we take 1,050 and we add it once, we get 1,100. We add 50 again, we get 1,150 for 2 standard deviations above. We add 50 again and we get 1,200 for 3 standard deviations above the mean. We also need to subtract 1, 2, and 3 standard deviations. So if we subtract the 50, we get 1,000. We subtract it a second time, we get 950. We subtract it a third time, we get 900. And the boss wants to know what percent of light bulbs will last between 950 and 1,150 hours. So notice 950 is here, 1,150 is there. Notice that's 2 standard deviations above the mean and 2 standard deviations below the mean. Remember, the empirical rule told us 95% of our data. So 95% of those light bulbs will last between 950 and 1,150 hours. So 95% is what we can tell the boss. On part B, the boss wants to guarantee to replace bulbs that last less than 1,000 hours. What percent of the bulbs would this be? Well, if we go back and look at our sketch again, here's the 1,000 hours. And he wants to replace bulbs that last less than 1,000 hours. So the ones that last less than 1,000 hours would be the ones below, this direction, to the left of 1,000 hours. Well, remember from our curve, we know that we had 13.5% of the data, 2.35%, and 0.15% in each of these sections. So we had 34% here, we have 2.35% here, and we have 0.15% here. Those percentages never change, so I've just copied them from our big picture above, and now we can just add those up. 34% plus 2.35% plus 0.15% gives us 16% of bulbs will last less than 1,000 hours. So if he's going to give a guarantee, he would be replacing 16% of those bulbs. Another example on the top of the next page. I want you guys to try this one. A vegetable distributor knows that during the month of August, the weights of its tomatoes are normally distributed with a mean of 0.61 pound and a standard deviation of 0.15 pound. So you've got room here. You can draw your empirical rule, draw your normal curve, and then answer these three questions. What percent of tomatoes weigh less than 0.76 pound, weigh more than 0.31 pound, and weigh between 0.31 and 0.91 pound? So pause the video and try this one now. All right, so when we draw our curve, we know, again, it should be a normal bell-shaped symmetric curve. We get the line down the center to represent our mean. We had a mean of 0.61. We know we're going to add 1, 2, and 3 standard deviations above the mean. We're also going to subtract 1, 2, and 3 standard deviations below the mean. Our standard deviation was 0.15. So we're going to take the 0.61 and we're going to add 0.15 3 times. So 1 time will give us 0.76, 2 would be 0.91, and 3 would be 1.06. We're also going to subtract the standard deviation 1, 2, and 3 times from the mean. So we end up with 0.46 when we subtract once, 0.31 for a second time, and when we subtract the third time, we get 0.16. So we want to know what percent of tomatoes weigh less than 0.76 pounds. Well, less than would be from 0.76 this direction. And so we're going to need to add up all of these. Remember, this was 34, 13.5, 2.35, and the last one was 0.15. Well, when you go adding them up, you should notice when you add the 0.15, the 2.35, the 13.5, and the 34%, that should get you 50%, which makes sense because that's where our mean is. That's half of our data. And so that 50 plus this 34 gets us 84%. So 84% of the tomatoes weigh less than 76 pounds, 0.76 pounds. Part B, what percent of the tomatoes weigh more than 0.31? Well, again, more than 0.31. Here's our 0.31. More than is going to be this direction. So we're going to need to add up all of these. Remember this one that we haven't filled in yet was 13.5, 2.35, and 0.15. And so you can add them all up. Remember, from here to the middle, you should get 50 plus the 34 plus the 13.5. You end up with 97.5% of the tomatoes weigh more than 0.31 pounds. And on part C, what percent of tomatoes weigh from 0.31 to 0.91? Well, 0.31 to 0.91, that's within 2 standard deviations above and below. You could also add the 13.5, the 34, the 34, and the 13.5, and you end up with 95% of the tomatoes weigh between 0.31 and 0.91 pounds. Right, the next thing we're going to look at is z-scores or standard scores. The z-score for a given data value x is the number of standard deviations that x is above or below the mean of the data. So to find a z-score for a data, it's how many standard deviations above or below the mean. So we have to find out first how far it is above or below the mean. And remember, when we do that, we subtract the mean, just like we did when we were looking to find the standard deviation. Subtract the mean from the data value. And then to find out that distance, how many standard deviations it is, we just divide by whatever the standard deviation is. So it's a two-step process. We usually look at it in a formula. So if I'm looking for the z-score, we call it the z-score for a particular x. So we put a subscript of an x on it just to let us know which z-score we're looking for. And so when we're looking for the z-score for that particular x, we're going to take that particular x and we're going to subtract the mean. And then whatever distance we get there, we're going to divide by the standard deviation. And so here's our formula for finding the z-score. Now, turns out z-scores do not have to be positive. If the z-score is positive, then that means when you subtracted, you got a positive number, you divide by a positive, and you still have a positive. And so that tells us that our mean had to be, that our data value had to be larger than our mean, so that when we subtract, we have a positive value. If it's negative, we'll come back and do 0 in a minute. If our z-score is negative, that means when we subtracted, we got a negative, because then we divided by the positive standard deviation and we still had a negative. In order to get a negative when we subtract, that means our x had to be less than the mean. It had to be smaller than the mean, our data value did. And if it's going to be 0, well, that means when we subtracted, we had to get 0. So that 0 divided by the standard deviation still gives us 0. And so to get 0 when we subtract, that tells us these two values had to be the same. That means our data value had to be the mean. All right, so here's an example of when we might use z-scores. Cheryl has taken 2 quizzes in her history class. She scored 15 on the first quiz, for which the mean of all scores was 12 and the standard deviation was 2.4. Her score on the second quiz, for which the mean of all scores was 11 and the standard deviation was 2.0, was 14. In comparison to her classmates, did Cheryl do better on the first or the second quiz? Well, we can find the z-score and it'll give us an idea of how she did relating to her classmates. It tells us how Cheryl's score was in relation to the rest of the scores. So we're going to have to find her z-score for both quizzes. The first quiz, she scored a 15. So we're looking for the z-score when the x is 15. And so we find it by taking the 15 and subtracting the mean. Well, the 15 on the first quiz, the mean was 12. The standard deviation was 2.4. So we subtract the mean and we divide by the standard deviation. So 15 minus 12, and then divide that by 2.4, you get 1.25. If you're going to put it in your calculator all in one step, you're going to need parentheses around the top. Otherwise, do it in 2 steps. Now, we also have to find her z-score for the other quiz. And on the other quiz, her score was 14. So we're looking for the z-score when the x is 14. So we're going to take that 14, we're going to subtract the mean. The mean was 11. And we're going to divide by the standard deviation, which was 2.0. So again, we subtract, and then we divide, and we get 1.5. So it turns out that Cheryl performed better on the second quiz in comparison to her classmates. So notice that both of her z-scores are positive. Both of them tell us she scored well above 1%, 1 standard deviation above the mean. And so she performed better than average. Remember, the mean is your average. So she performed better than average on both of these quizzes, the average of her class. But since her second z-score was higher, that tells us that she performed better on both. She performed more so on the second one. So I know it isn't good grammar, but her z-score on the second one being higher says she performed more better than average on the second quiz. Again, I know it's not good grammar, but what I'm trying to say is she did better than average on both. She did more so on that second one. More better than average. She performed better than average on the second one compared to the first one. All right, another example on the top of the next page. A random sample of 1,000 oranges showed that the mean amount of juice per orange was 7.4 fluid ounces with a standard deviation of 1.1 fluid ounces. Determine the z-scores to the nearest hundredth of an orange that produced the following amounts of juice: 6.6 fluid ounces, 7.4 fluid ounces, and 10.9 fluid ounces. So pause the video here, try this one on your own. Okay, so we're looking for a standard deviation. We're looking for a z-score for all three of these. So for the first one, we're looking for the z-score of a 6.6 for our data value. So we're going to take the 6.6 and we're going to subtract the 7.4. We're going to subtract the mean, which was 7.4. And then we're going to divide by the standard deviation, which was 1.1. And that gives us a z-score of negative 0.73. Is it okay to be negative? Sure. And it turns out this one, we expect it to be negative because our value was less than our mean. The orange we had was smaller than the average orange, so we would expect its z-score to be a negative. And so negative 0.73. Remember, we wanted the nearest hundredth. That's 2 decimal places, and it's going to be very, very important that you round these z-scores correctly. On the next one is 7.4 fluid ounce orange. Well, notice that's the same as our mean. So we're going to expect a z-score of 0 here. And notice that's what we get. If we take the 7.4, we subtract the mean, we divide by the standard deviation, we do get 0. Now with an orange that's 10.9 fluid ounces, that's larger than our mean, our average orange, so we would expect a positive z-score here. And so we find the z-score by taking 10.9, subtract the 7.4, divide by the 1.1, and we do get 3.18, rounding to the nearest hundredth. All right, we will continue this video in part 2. For part 2, you will need the table that is with the notes. Make sure that you print it out and have it handy for the rest of these notes.